Okay, welcome everybody to Watershed University. We're going to be talking about flood warning systems and hydrologic warning systems. I'm going to use those terms interchangeably, so if you see one, the other actually applies as well. Today's presentation of Watershed University is organized by DWR and the California Silver Jackets, so we much appreciate their efforts. And again, I'm David Curtis from West Consultants, also representing the National Hydrologic Warning Council. I'm going to cover an awful lot of material today. It's going to be a quick spin through the full spectrum of flood warning systems, and we're going to cover issues related to planning and design and operations and maintenance and a few odds and ends at the end as an overview. So strap in tight, hang on, it's going to be a fun ride. Okay, the primary goal of any hydrologic warning system is to save lives and property. One of the issues when you develop a hydrologic warning system is that floods or any kind of hydrologic hazard tend to happen periodically and sometimes a long time in between incidents. So what you have to do is think about other applications for the flood warning system to maintain continuous interest throughout the lifetime of your system. And that may include secondary purposes like hydrologic data collection and archiving of that data that might contribute to hydrologic design standards down the road. And it may serve multiple purposes like recreation, water quality, and so on. When you're dealing with a hydrologic warning system, the whole process tends to be a circular process. And the first thing that you have to do is identify the hazards that are in front of you. Once you've figured out what can happen, then plan for a way to respond and deal with those hazards as they occur. Once you've done that, you need a method to detect when you're about to get hit by one of those hazards. And then be able to identify what triggers and signals that you can detect that allow you to forecast what's going to happen next. Once you have a forecast, it needs to get disseminated to the right audience and right people. And then the plan comes into play in dictating how your community responds to the flood. Once the flood response has finished, you move into recovery phase, then review what the heck just happened to us, figure out how to do it better, perhaps reevaluate your hydrologic assessment again to decide that, you know, if that was the second 100-year flood in this week, maybe that wasn't a 100-year flood, it's something else. So you need to reevaluate that and incorporate that into the planning process, and you start the process anew. Here's another look at that same process, only superimposed on a flood hydrograph. Kind of in a condensed version, you've got planning before the flood occurs. You have to identify the threat, respond to that threat, recover after the event, and then go through the planning process again. Some of the issues that we want to cover, and a lot of what you'll see today, is how to deal with the flood threat recognition and response side of things. And the whole objective in this part of the process is to move the line for early detection of the threat further to the left, in other words, earlier in time. And that allows you to move the response initiation further to the left as well, and you'll have more time to respond. So more time to recognize the threat and respond to the threat is what you need to actually mitigate the damage that might otherwise occur if you had no warning at all. On the planning side of things, we need to identify our existing hazards, figure out some sort of risk reduction strategy, understand what the community's capabilities are. Human elements are extremely important in understanding response to a developing emergency. The all-important emergency action plans, and of course cost and funding issues down the road. In the planning cycle, you have to identify your existing flood hazards, and that begins by identifying what type of hazard are you dealing with. Is it primarily an urban environment? Is it a mountain flash flood kind of situation, large rivers, or a dam and levee, or some other physical structure that's an issue that might overtop or fail? Coastal flooding has become more and more on people's minds as we deal with issues like sea level rise and climate change. You need to consider the history of flooding in your area, or what kinds of hydrologic hazards have been occurring and their frequency. You may be looking at modeling results, either current results or past studies that have been done. And then you need to identify what trends might affect how you're developing hazard. And by trends, that could mean development in an urban watershed or climate change affecting the mixture of rain and snow in California, for example, in our mountain watersheds. To develop a strategy, you need first to develop a vision and goals. What are you doing with this flood warning system? And that's going to depend a lot on your situation and what type of flooding and where you're located. Located on a coast, or are you a mountain community? You need to understand kind of the warning process tripod, if you will, or a three-legged stool. With one leg being the observation, monitoring, detection, forecasting, and generating of warnings. The next leg is disseminating that warning out to the public, and then being able to respond appropriately is the third leg. If you miss any one of these legs, you're not going to have a very stable stool, and you'll have problems in the long run. You may start small and expand over time if you're starting from scratch with a new system. You don't have to put the complete system all at once, but you can get started. Putting that first gauge in, or first monitoring, or first effort step forward is usually the biggest bang for the buck, so it's important just to get started. And at the end of the day, public education and outreach is absolutely critical to system success. The more you can do to engage your community in the process and get them to understand what's going on in the basin, the better off you're going to be. The planning side, again, understanding the community capabilities and infrastructure is really critical. I highly recommend leveraging all of the existing monitoring and telecommunications systems that you can possibly find. I frequently get shocked at how many capabilities are out there that are all existing independently and just need some kind of framework or mechanism to kind of bring them together under one roof or one common framework so that the information can be shared. As a good example, we're doing a gauge study in a basin up in the state of Washington, and we had what we thought was maybe 100 or so sensors in the region. What we ended up finding was over 4,000 different hydrometeorological sensors that were currently in operation and that were somehow available on the internet. So look into those capabilities, because you may find there's an awful lot more there than you imagine that can be leveraged as part of your warning system. Understanding who, what, and where of your emergency preparedness capabilities is critical. More people die in cars and in transportation systems than just about anything in a flood. And so you have to understand what's going on with your transportation system relative to hydrologic hazards. Knowing where the critical facilities are, hospitals, police stations, fire stations, schools, and the like, is a really important part of it. And GIS is your friend, because most communities now have really sophisticated GIS capabilities that can be a great utility in developing your plan. Understanding the human element is another really important piece to the puzzle. It turns out people are motivated in similar ways during emergencies, but the demographics in your region can have a really big impact on how and where and when you can communicate to your population segments during an emergency. You have to really understand your media outlets and who their audiences are, what languages are prevalent in your area, and how do you get to those folks. What kind of communications tools do they have? Are smartphones prevalent in your audience or not? And social media has rapidly grown as a really critical tool for emergency managers in recent years. Not just presidential tweets, but it's really important to get out there, and these tools have become vital for communications. A really great example is the work that the National Weather Service has done over the last 4 or 5 years with emails, Facebook, and Twitter feeds. Here's an example of how the National Weather Service has completely reconfigured their communication tools in terms of text messages. In the past, they would start with a weather summary, which you now see down at the bottom, and the meteorologists would talk in meteorology speak. Most people would be bored silly by the end of the message. Most people would get bored silly by the initial discussion and not even get to the impacts and what might happen later on in the message. Now the Weather Service has completely turned that upside down, and they start with what's going to happen. Hey, there's a wet pattern that's going to come in this weekend. What are the impacts? How confident are our forecasters in that message? What's the timing and strength of the event that's about to happen? Then they get into meteorology discussion. So it's really a big transformation about what they've done and how they actually communicate. They've taken to developing infographics. So here's an example of the text message converted to an infographic where you talk about timing, the threats, and some tips about the upcoming threat. And here's yet another example where the same information is in a more sophisticated infographic where you basically have a graphical representation of the impacts, the confidence, the type of impacts that are going to occur, and a timeline on when they're going to occur. You know, you may be traveling up in the mountains around here and it's raining on Friday, but then snow on the way back. Completely different impacts that may affect your travel and safety. And then they're putting out graphical representations of the precipitation forecast, for example, or it might be a temperature forecast or wind gusts, but presenting them in a really graphically powerful way to communicate what's going on. And it's really important for your local plan to leverage these kinds of tools because they're very, very powerful communication applications. A key point about social media is a lot of people, in order to determine whether or not they're going to respond to a particular flood, look for confirmation. And they might be their neighbors and it might be a relative, but the more social media out there and more people are on social media, so many people are getting the same message that it's much easier to get confirmation amongst your audience. Twitter, this is a great example of the use of Twitter. Whole systems out there now actually tweet messages. And you can basically see examples in the text stream here of the Schuylkill River, which is outside of Philadelphia. And you can see at 8 o'clock in the morning on the 14th of July, the river was 2.92 feet and rising. An hour before that, it was 2.69 feet and rising. An hour before that, it was 2.41. If you look at the insert, that's my Apple Watch, and you see Schuylkill River a day later, it was 4.46 feet and falling. So you can actually get these messages right to your watch and be able to monitor what's happening in different watersheds. Emergency action plans are extremely important, and it's important to remember that Run For It is not an adequate emergency action plan. In fact, failing to plan is actually a plan to fail. It's important to understand that EAPs can and should be prepared whether or not you have a flood warning system. But they're absolutely critical if you do have a flood warning system, and they should cover all of the hydrologic hazards that your community might face, including the thresholds and trigger events and responses to each one of those hydrologic hazards. The flood warning system needs to coordinate and link directly with the EAPs, and most importantly, practice, and frequently update the plans to keep current with evolving technology and evolving conditions in the community. Costing and funding is always a critical thing to pay attention to, but one of the first things that I always like to see is a champion for the system that's involved locally. And this is somebody or a department that's got a vested interest in the data, got some technical skills to understand the flood models and the underlying hydrology and hydrologic processes. But that champion for the system is somebody that has a passion for it and understands the implications and the value to the community and can be there on an ongoing basis to ensure support over the long term. Developing a planning level cost estimate is key, and we'll get into that as we go through some of the different issues that are related to what costs money and what doesn't. A really important component for cost and funding issues is the Federal Emergency Management Agency's community rating system for flood insurance. The really important thing to remember is that you get credit, your community gets credit for the implementation and operation of hydrologic warning systems. And that becomes valuable political leverage to encourage your local community leaders to participate in a flood warning and invest in a flood warning system. City of Roseville here locally in the Sacramento area is the top CRS-rated community in the country, and each one of the people in their floodplains receive a 45% reduction in annual flood insurance premiums. And by implementing a flood warning system, you can actually gain enough points to maybe go from one class to the next, which by itself is a 5% reduction across all of the policies in force in the basin. So it becomes a very, very powerful political tool. The CRS system is 600 series. If you get into the manual for floodplain managers under warning and response, and so the 610 series is flood warning and response systems. 620 is associated with levees, and 630 is associated with dams. Each one of these activities, floods and levees and dams, all have common elements: threat recognition, how to get the warning out, the plan for that, and how to coordinate with critical facilities. It's really important to remember that each one of these elements, flood threat recognition, early warning system, dissemination, flood response operations, and critical facilities planning, each one of those has a whole series of criteria that you need to satisfy in order to gain points under each one of these categories. Those four that have the asterisks beside them, you need to have points in every single one of those, at least some points, in order to get credit for any of them. So you could max out under flood threat recognition, early warning system, and flood response operations, get all the points available, and if you don't know where your hospitals and police stations and schools are, you'll get nothing out of the whole effort. So it's important to have some points in each one of those individual categories. And a couple other areas that you gain points for your community is to be involved in the National Weather Service's Storm Ready Community and Tsunami Ready Community if you're on the coast. Each of those have specific standards to achieve in terms of having local focal points for warning, hydrologic warning, or tsunami warning in the communities, or even broader aspects under Storm Ready. It can be any kind of storm system that the National Weather Service is concerned about. So those are two other avenues to get additional points. And the maximum number of points that you can achieve is 395 under the 2017 criteria. And it turns out that that number 395 is going to be very important to you later on. So take out a pencil, write it down, because you may need that later at the end of the end when we have a test. One of the key elements of flood response operations under the FEMA requirements is floodplain mapping. So, and it has to be tied to the individual stages in your locality, so you have some idea at each level of flood hazard how much of the community is going to be affected by inundation. When you have these maps, you need to have different, they all have to be tied to different actions, for example. Flood warning systems or emergency response systems often are color-coded, where you have, in this case, green, orange, blue, red, or black, which indicates the level of severity from minor to all the way to the maximum. At each category, you may have a whole series of things that you plan to do. So if you're in green, you do A, B, and C. If you're in the orange, you do C, D, and F. If you're in blue, you do E, F, and G. And basically, that's the kind of information that will appear in your plan and needs to be thought out ahead of time. When you're doing planning, it's often good to kind of go back and review what's happened in prior storms. And this is an example of a couple of storms and a write-up about what happened how severe was the event, what was the nature of the evolution of the storm development, how frequent was it, was it a 5-year event or a 500-year event, what happened with the local streams, how deep were they, what was the extent of the flooding, and more importantly, what was the community response. Then you go through and look at your existing networks in the area, identify what's available to you, what's reliable, what's not, how can I get it automatically in real time. Where are my historical flood areas? Get those things identified, understand what was the cause in those areas. Look at the roadways, bridges, low water crossings are really important and key hazard flood event. And when you identify those high-risk areas, then dig a little bit deeper and look at what are the causes, what's going on, what are the triggers, and identify what responses need to happen in each one of those cases and include that in the plan. When you get into the design of flood warning systems or hydrologic warning systems, there's a series of elements that you need to consider. What kinds of instrumentation is needed, from precipitation forecasting, monitoring rain gauges and stream gauges on the ground. How do you communicate? What kind of computer systems and IT infrastructure do you need? And is there some sort of forecast modeling that's required as well? Just a note to talk about some of the issues that are a little bit different from forecasting as opposed to design, for example. If you're dealing with flood forecasting, I like to refer to it as making life and death decisions before you have all the facts. And you don't get all the facts about a flood till you get all the way over to the right-hand side of that blue hydrograph that you see on the screen. But that's way too late to be issuing a forecast. You have to be issuing the forecast much earlier in the process. If I wait until the peak of the flood to issue a forecast, I might have a very accurate forecast. I can tell you exactly what's going to happen right at the peak. But it doesn't have any value to your community. On the other hand, if I'm too far ahead of the event, and I'm so far ahead that I don't have any credibility of making a forecast that far ahead, it also has low value. Someplace in the middle, there's a sweet spot where I've waited long enough to see the development, the early stages of development in the event, that I have enough information to produce a credible forecast that your user community can have enough confidence in to actually take beneficial action. So in the flood warning business, it's a constant trade-off between accuracy and timeliness. They're pretty much incompatible. And so you have to find kind of that sweet spot in the middle where you get a nice balance of each. Flood warning systems have a whole bunch of different moving parts. Off the left-hand side of your screen, you may have a whole variety of remote sensors out in the remote parts of your watershed. Because they're remote, you need to figure out how to get it from those distant locations into a computer system at a central location. You have to be able to communicate with your flood warning system operators, emergency managers, and other agencies like the USGS, the Corps of Engineers, or the National Weather Service. You have to be able to communicate with the media. And most importantly, you have to engage the public. And as you can see all those arrows crisscrossing the entire screen, there's a lot of multiple communication directions between and betwixt all the different players in the process. One important thing that I like to emphasize when dealing with the public is the fact that quite often we engineers and scientists tend to underestimate the ability of the public to understand what's going on. Sometimes decisions are made to withhold information from the public because, well, the public's they're not trained engineers, they're not trained hydrologists, they're not trained meteorologists, so they may not understand or how to interpret this message. Most of us are familiar with the TV broadcast where you see Doppler weather radar and animations of Doppler weather radar on the screen, and we can't imagine those kinds of presentations without animations of radar or satellite imagery. When that was first introduced, there was a big outcry in the meteorology community that the public was not prepared to interpret them. And what actually happened is the public figured out that when that big red blob was headed toward their house, they knew it was going to rain quite hard in a few minutes. So we too often underestimate how much or how capable the public is to learn and understand about what's going on. We just have to be open and communicating and continually educating the public so that we can help them out in that process. But I'm a big advocate of getting more out to the public than not. Gauge design, network design is a key part of any sort of flood warning system. Enough, some of the hydrology factors aren't at the top of the list. Accessibility and security are probably at the top of the list. You need to be able to get at your sites and maintain them. They have to be secure so that they don't get vandalized all the time and therefore not available when you need them. And then you get into some of the hydrological factors. What kind of flooding are you dealing with? Is it a big riverine flood that slowly develops over days or weeks, or is it a flash flood event or an urban environment? What's your topography like? Are there reservoirs involved? Those are the kinds of questions you need to look into ahead of time. What's the density of gauges? I get that question all the time. How do you distribute the gauges over the watershed? Is there a way to optimize, and what's the cost? Well, when you kind of put it all together, every optimization study I've ever seen has always come up with the same answer. The number of gauges required to optimize the sensing of rainfall data is always larger than your budget. So your budget kind of becomes a limiting factor, and Dr. Dave's rule of rain gauge network design is simply buy as many gauges as you can afford to maintain well. It's better to have a few really good quality gauges than a whole bunch of gauges out there whose data you don't trust. So it's important to basically get gauges out there and be able to maintain them, and then add gauges as your capability and finances allow. You may consider co-locating with other agencies like the USGS. And there's a fairly significant move to what we call citizen science, and it's volunteers with gauges out there that might be able to help as well. You have to go into that with your eyes wide open to make sure the data is the quality and the reliability that you need, but it's an important enough source now that it's worth mentioning and thinking about. On the precipitation and monitoring side, satellite and radar can be very, very useful. Out here in California, we do have some challenges with things called mountains, which tend to get in the way of radars, but there are areas where radar is extremely effective, particularly here in the Sacramento area in the Central Valley. Very, very useful. You can either use qualitative sense in terms of figuring out, the red there means it's raining really hard, blue not so much. And where are those red cells going? Okay, those are important things to be able to monitor. You can also link them to automated gauges in the field and actually bias correct the radar data, so that becomes a useful quantitative tool as well. Similar with stream gauges, you may want some automated gauges out there to be able to tie into a forecast or simply monitoring when things get critical, when bridges go out of service or roads go out of service or community facilities become threatened. Excuse me. There are tons of different kinds of water level sensors out there that will become part of the equation, and it depends on the type of locality you have, type of hydrology and hydraulics that are there. That'll dictate which of these you might use. But you have pressure transducers, which are simply sensitive to the depth of water over that site. Bubblers are a little bit different. They just the same idea, looking at pressure, but looking at releasing gas into the stream and measuring the back pressure and relating that to the depth above the bubble release point. You may have something called a stilling well, which is simply a 1 to 3 foot diameter well that serves as a device to still or quiet the water surface, so you can put a float on it, which rises and falls, and you can measure that rise and fall and transmit the data to a central site. There are radar and ultrasonic sensors which use electronic or sound waves to beam down to the water surface and measure the return time, and then you can relate that to water depth. Each has their own strengths and weaknesses, and you kind of have to sort out what's good for your particular location. Where do you put them? In case of a bridge, is on the upstream side or the downstream side? Probably the preference is to put it on the upstream side from a hydraulic control perspective, but if ice or debris is an issue, you may be forced to put it on the downstream side of the gauge simply for protection so it doesn't get ripped out at the first ice jam or breakup or the first debris flow that comes downstream. You may need to do some things for impact protection for the same reasons. Considerations are important. As we mentioned earlier, access and security is important. Data accuracy is not only important when you install the gauges, but you kind of have to pay attention to what happens over time. That cute little bush that was there next to the gauge 20 years ago is now a 40-foot high tree with branches over the gauge. And that will dramatically affect your gauge catch and the information that you get. So you need to be paying attention to those kinds of situations over time. The type of housing, is it shared housing with other agencies like the Corps of Engineers? Again, those are site-by-site decisions that can be made. If you have a bunch of gauges out in remote areas, you need to figure out how to get the data from the remote sites into a central computer or some other device to receive that information, and there are all different kinds of protocols, alert being a common one out here in California. I will get to that in a minute. Landlines, those are a possible source of data communication, or internet-enabled devices that connect directly to the network. A whole variety of wireless kinds of communication, VHF, UHF radios, cell service, satellite, microwave, different kinds of microwave, spread spectrum radios, and then you'll need repeaters if you have a really long distance between a remote location and a central site where you're collecting the data, especially if there are things like mountains that get in the way and you don't have good line of sight between the remote location and the central receiving station. I mentioned alert, and I bring that up because alert is a very, very prevalent system here in California. And alert actually stands for Automated Local Evaluation in Real Time. It's a technology that's now 40 or 45 years old, and it's based on the principle of event reporting. And in the case of a rain gauge, an event is defined by a tipping bucket that actually tips. So if you see a little schematic on the right-hand side of your screen, see a funnel with water dripping into the one side of a tipping bucket. That side gets full, it gets heavy and tips over, and the second bucket comes up underneath the funnel and begins collecting again. Most alert gauges in California are sized to tip after every 1 millimeter of rain. The really nice thing about this approach is that they were designed for flash floods. So the faster those buckets fill and tip, the more frequently the transmitters report the information. So what you have is a system whose reporting rate is directly proportional to the intensity of the event involved, and that's really critical for flash floods. Here we have 1, 2, or 3 gauges reporting their messages, and you can each one of those blue blocks is a message that get transmitted. All of the gauges operate independently, so every once in a while you'll get a collision where two sensors arrive, or two messages arrive at the central receiving station at about the same time. And that's one of the drawbacks of alert. In the early stages, where there weren't that many gauges, it wasn't a big problem. But as areas got saturated, like Southern California, for example, it has over 1,000 of these operating, the performance started to degrade, and we've gone to a new type of system called Alert 2, which has been implemented over the last, well, it's currently in process, but it started about 5 years ago. And that, instead of having all of the gauges reporting randomly, there's some discipline involved in the transmission process so that there's no longer any overlap. In addition, the new protocol adds some error detection and correction capabilities so that if somehow the message was corrupted slightly in the process of going from point A to point B, the systems are smart enough to figure out which bits got changed and can reconstruct the original message. So it's a really big step forward in terms of quality of data transmission and reliability. At the base stations, you need to be looking at the software first. It's like decide what kind of software you need and then figure out what kind of computer you need to run it. You need to be able to receive all the data from all the different telemetry systems, and there can be multiple telemetry systems in use. Be worried about data storage or analysis and forecasting. Alarm functionality, communications with other emergency systems is critical. You need to avoid single points of failure, so component redundancy is critical. You need redundant computers, 2 is a minimum. You may incorporate virtual or cloud configurations over the internet as well. You want to co-locate or be at separate locations for your redundancy. Clean and secure power is really critical. Power can get really noisy and be very damaging to electronics. And you also need to be able to have data and voice communications with emergency managers through your system as well. On the hydrologic forecasting end of things, we can talk about all different kinds of inputs. We may need to have forecasted rainfall. We need to consider our watershed models, how to move the water through the watershed, maybe through a reservoir, and then some of the more advanced characteristics to consider are probabilistic forecasts that go out even up to a year, depending on what kind of hydrologic forecasting that you're dealing with. Inundation mapping has become an extremely powerful tool for getting information out to the public, and it's an incredibly powerful visual tool to help people understand the areas that might be inundated and when they might be inundated in the community. Operations, and that includes staffing, installation, maintenance, data assessment, funding, communications, coordination, flood forecasts and warnings, and a whole host of other issues. So we mentioned earlier, have that champion in place, in-house staff. You need to have some folks that understand hydrology, hydraulics, some techs for maintenance. IT has become increasingly important, especially with cyber security issues to worry about. Consultants can be a big help, and technical and systems support, developing forecasting tools. Vendors are an important resource for equipment and technical support and O&M. And then your partners like the Weather Service and the Corps and USGS are really vital contributors to flood warning systems. Staffing is critical. Staff depth is important. When you get into floods, you might be going 24/7 for several days. So you need to have enough capability to be able to staff at that level. One field technician under ideal circumstances can manage about 30 to 40 gauges, depending on how big the area is that you have to travel, the difficulty in terrain, and how frequently they have to be visited each year. More than likely, your safety officer is going to say that one technician shouldn't be out by himself, and you should have 2 at all times, and that's not a bad idea. IT has become increasingly important, and so you need to have IT specialists that understand what you're doing, and somebody that understands hydrology and an engineer is vital, and you can actually contract out some of the work, and I actually support a couple of systems that way. On the installation side of things, safety is paramount. You want to look at how, in terms of a rain gauge, where can you locate the gauge to get good reliable catch through all different kinds of storm conditions. And then if you're out surveying, we need to be able to understand what are the benchmarks? What are your elevations of the gauges? How do they tie into local topography and other mapping systems? Identify the top of bank and what key landmarks are underwater at a given stage. Looking at the individual sites, there are housing considerations. How do you want to store the electronics? Do you co-locate with another agency like the Corps or the Corps or USGS, for example? And then locating it in a spot that's not going to get damaged the first thing when you have a major flood event. Maintenance issues requires regularly scheduled and emergency maintenance, so you need to be able to prepare for that. And the field work can cover a whole host of components that are out in the field. You need to be able to calibrate your instruments, and you need to be able to get them to at least once or twice a year, maybe more depending on your situation. Field components, you have all the different types of sensors. Here's a weather station that's got antennas and solar panels and wind, barometer, precipitation, and then the electronics packages all to worry about. And we talk about repeaters, and again, if your gauges are far away from the base station, you need to be able to relay that signal into a central location, and you need to understand the radio propagation characteristics of the region. On the maintenance side of things, kind of some of the other issues to pay attention to, just what material do you need, equipment, and the vehicles needed to get out there, what training and safety training do you need for your staff, safety equipment, being able to keep everything up continuously, what things do you have to do to maintain your CRS compliance, the community rating system, and being on the lookout for continuous system improvements. And the base station side, again, same kind of thing. It requires regular care and feeding. The data management is going to cover your servers, software, and your websites, which is a really critical feature. When you're looking at the data, you need to be able to look at it and make sure that it's accurate and you're getting the data from all the sites reliably. You need to be able to manage the data both in short and long-term storage so it has value long-term, and understand how the data can be shared not only with other agencies, within your own agency, or with the public. Long-term funding is a really critical thing, and it's probably the greatest barrier to long-term success. O&M costs can be high, but the savings are immeasurable long-term. So I highly recommend looking at your system and promote its use in other areas, be it water quality, supply, reservoir operations, ag support, whatever it takes to actually increase the audience for your system. O&M costs, kind of a rule of thumb. You can see at individual gauges, as the Harris County Flood Control District is on the order of $4,000 to $6,000 per year. USGS gauges, something on the order of $15,000 to $20,000 per year, and you can see some installation costs. Some facilities like the Maricopa County in Arizona, their budget's on the order of $2 million a year. They're maintaining over 300 sensors in their flood warning system there. Communications are important prior, during, and post-flood event. You basically have to figure out your roles internally, understanding who your partners are, figuring out how to share data, and then being able to document everything that you do so you can repeat the process in the future. The flood forecasting methods are something to consider. There are a lot of packages out there that are available off the shelf. A very common one is a real-time system from the U.S. Army Corps of Engineers, Hydrologic Engineering Center. Locally, the city of Roseville is using a variation of that to forecast their flood events. San Diego County is also using RTS to develop not only the flood forecast, but also stage forecasting and inundation mapping. When you're dealing with a flood forecast, basically you have to understand where it's going to flood, what will flood, how high, when, and how long. And then when you're giving a flood warning, what do you say, to whom do you say it, when are you going to say it, how do you communicate, and most importantly, how do you coordinating your messaging with the National Weather Service so that you're not on a different page and get cross purposes with the Weather Service in their messaging as well. When you get to the end of the flood or near the flood, documentation, flood photos, high water marks, counts of houses that were flooded, and a whole host of other information. And this becomes really, really important if you can get your hands on this information when it comes time to document for emergency declarations and FEMA funding to help the recovery process. Having a good database of this kind of information is really critical in the long term for a speedy contribution from FEMA. And then to kind of begin closing here, we've got additional resources. The National Hydrologic Warning Council is a really important organization it's the only professional organization solely focused on hydrologic warning issues, and here's their website. A really good document about early warning systems can be had from the National Weather Service in their training center. The website is there. You've got the USGS that has a whole host of different kinds of material, and then some citizen science type activity from something called COCORAS, which is the Community Collaborative Rain, Hail, and Snow Network, and there is their website as well. For additional information, we can contact myself and with my email address and phone number there, or Steve Fitzgerald, the current president of the National Hydrologic Warning Council. And I'll leave you with the notion that flood warning systems really do work. Here's an example of Colorado in 2013. In 1976, the Big Thompson Canyon, not too far from Denver, had a major flood event, and 140 people died that day. 2013, they had a big event over the entire region, much broader extent, much higher population, and with the warning systems and other flood mitigation activities they've undertaken in recent years, the total number of deaths was 8. A significant improvement. Take a look at tropical cyclone Phelan, which hit India, the northeast coast of India in 2013. Turns out that a virtually identical major tropical cyclone, Orissa, occurred in 1999, causing 10,000 deaths. The implementation of a good warning system reduced that to 50 deaths in 2013 from a similar sized storm. And although 5,000 people died from Typhoon Haiyan in the Philippines in 2013, warning systems were able to effectively evacuate 750,000 people. So these are really good examples of that flood warning systems can work, and you can have a tremendous return on the investment for their implementation. And with that, I'll close and let the guys open the door for questions.